Welcome to another session of microengineering. In today's lecture, we are going to learn about traveling wave tube amplifier. It is also an O type of tube. The first thing that comes in our mind is that how do we compare it with klystron? Because both are amplifiers. Two cavity klystron is also an amplifier. Traveling wave tube is also an amplifier. The first degree of comparison is that wave in a traveling wave tube amplifier is always propagating. Meaning, in klystron when you had seen, the wave was always there, present only in buncher cavity. It was the electron beam which was interacting, and then that energy was getting collected at your buncher cavity, at your catcher cavity. The wave was not propagating in klystron, whereas in TWTA, wave is going to be always a propagating wave. Secondly, coupled cavity TWTA, there is a coupling effect. This is not there for you all. We are just going to take TWTA. Whereas cavity over klystron is going to operate independently. Remember, klystron always have re-entrant cavities. Do you recollect that? Resonating cavities. Here, the resonance property will not be there. That they will be. In fact, we are going to have a new cavity called as slow wave cavities. Okay, slow wave structures. Alright, what is the characteristics? It works greater than 3 gigahertz, right? Bandwidth is about 0.8 gigahertz. Efficiency is 20 to 40%. There, the efficiency of klystron was hardly 25 to 30%. Power output is 10 kilowatts. There, it was 3 kilowatts. Here, if your power gain is up to 60 dB, excellent, because their power gain was hardly 30 dB. I'm comparing it with klystron because both are going to act as an amplifiers. What is the speciality of these slow wave structures? We do not have resonating reentrant cavities in TWTA. Instead of that, we have helical structures. What are helical structures? Meaning slow wave structures. I'll explain what is happening over here is that you need the electron beam to interact with RF wave because the RF wave amplification has to take place. So electron beam will move at a maximum velocity of how much? DC electron velocity. If you recollect the formula, it was always small v naught. Do you remember this, everybody? Small v naught. And that small v naught used to be 0.593 into 10 to the power 6 into square root of v naught. Meaning it can depend on how much? It can depend on square root of it. How much can you give? How much cathode voltage can you give? We have a limitation because maximum voltage we give is from the AC power supply. We have a power supply. Only that much we can give. We have a limitation of that. Whereas your RF wave is propagating with velocity of light. So your RF wave has to slow down. So what do I do? Allow that wave to pass through some structures. That structures are called as slow wave structures. They can be helical in shape. They can be interdigital. They can be different shapes. We are going to take a helical structure for you. And that is why we have made a diagram. This is called as pitch. That is the distance between the two. You can see the diagram is made something like this for you all. This is the distance between two helix structure. This is the circumference which we take, and we have the property. We say that the by how much will your propagating wave reduce its speed? We say it is c multiplied by this pitch upon square root of p square plus pi d square. By this much, having more the number of turns, maybe you can reduce the velocity at which your wave is propagating. This is how the helical structure looks like. This is how the helical structure will look like. In a helical structure, you will be having, you can see over here, you will be having the helical structure over here. Can you see, everybody? I'm just marking it red color. This is the helical structure we have. These, don't get surprised, these are your solenoids or your magnetic focusing. You can have electrostatic focusing also. These focusing is to make sure that the electrons are not deviated out. The electrons are always following the linear beam. And remember, these are O type of tubes. O type of tubes, it means electron beam and the electron beam and your RF velocities are trying to move in a same path, linear path. This is a cathode supply. We are having different voltages. We are trying to control the amount of energy that will be generated. Please note that the gain generated by this was 60 dB. How do you think it came 60 dB? By increasing the length of the tube, you can increase the gain of the amplifier. This is how interaction takes place between your electron beam and RF wave. This you have already seen in klystron. Positive half cycle, what happens? Positive half cycle, you are going to have accelerated Negative half cycle, you are going to have a retarded field. Zero cross section will be always your no change in velocity. So this is how your RF and your things can. The same things which were explained in the diagram is been written over here. But remember, there is something special also in this. An attenuator is being placed near the center of the helix. If you have seen the diagram, when we have drawn the slow wave structures, have you seen we have not drawn it continuously? There was something like this. Something came in the middle and then the continuation was. You can just see the diagram again if you want. This thing which we have drawn, is called as an attenuator. The function of this attenuator is that you can say load reflection takes place, it will not allow to come back to the source. So your source is always safe. That's a function of an attenuator. And secondly, that is what it reduces all the waves traveling along the helix to nearly zero. The back one. So the reflected waves from the mismatched loads can be prevented from reaching the bottom. This thing is also equally important. This is the function uh, of an attenuator.